Good afternoon. So just to make sure, this is CS162. And so I guess everyone here is for CS162. So I am Ion Stoica, and I'm going to teach this the class this semester. So we are going to spend some time together. And just to give you a little bit of background about myself, I guess my research span quite a bit of networking distributed systems. And I start with networking, working on quality of service and network architectures. Some of the projects, more recent projects, is Internet indirection infrastructure and declarative networks. Then I did some work on peer-to-peer networks. Some of the projects there are CORD, and again, Internet indirection infrastructure spans both the peer-to-peer and the networking research. Then more recently, with actually these guys who are here TAs, I'm doing some work on cloud computing. This is the most recent work I'm doing, scheduling resource management. The projects will be, our Nexus and Spark, and hopefully we are going to talk a little bit towards the end of the class about them. And I also am focusing on debugging and replaying. So the question here is about how you'll be able, once you have bugs in systems, especially in particular in distributed systems, how you are going to be able to reproduce these bugs and eventually to find solution for those bugs. Okay, any questions so far? So I hope to get many questions, especially at this time of the day. Will help all of us to have a more engaging lecture. So the goals of today's lecture, it's to say, to kind of understand at some level, it's again the first lecture, what is an operating system and what is not. And going a little bit through some examples about operating system designs to see what problems the operating systems try to address, what are the challenges in addressing those problems, and what could be some potential solutions. And of course, this is a good question always. Why do you study something? I mean, to graduate, that's a very good answer. But beyond that, why would you be interested to study the operating systems? And we are also going to talk about some logistics today, of course, about what are the expectations and how this class operates. And please, interactivity is very important, so at any point, just ask questions. So I think that one of the main, the next slides are about a few trends which makes operating systems interesting in particular, and the computer science interesting in general. And one of these trends is Moore's law. How many of you heard about it? Of course, very good. So this is a very, it's an amazing law because, there wasn't a lot of science behind it when it was given. So Gordon Moore, one of the co-founders of Intel in '65, it seems it was at a conference, was asked about, what do you think about, the number of transistors in a chip and how they are going to evolve over time? As any good computer scientist, Gordon Moore, took a piece of paper, he plotted here some points, the previous years, and then again interpolated. Okay, so it seems a line. It's you notice that it's a log scale. Okay, so this means that on the y-axis you have a logarithmic scale, and it's a linear on the x-axis. So if you have a line in such a plot, what does it mean, a line in a logarithmic plot? The increase is exponential. Okay? So basically he deduced, based on the data he had here at the beginning, that the number of transistors on a chip will double every 1.5 years, 18 months. Okay? And as you see, this is, over more than now 4 decades, this law pretty much holds. Yes?
Intel,
Excuse me?
they're all from Intel, so they're just following what their boss says.
Yeah, that's good. So that's good observation. But again, if you look at the other processors, they are in the same ballpark. And actually, at some points when it used to be a higher competition on the processor, in the processor market, when, DEC had their own processor, HP and IBM was more active, actually those processors, they were having more transistors usually than the Intel's one. Okay? But again, some people say, this is a self-fulfilling prophecy because, you know that you need to double it. So this is a good, from the marketing perspective, it's a good thing to have. But besides that, the ability to double this number of processors every 18 months, if you take a step back, it's quite amazing. Okay? And there are very few disciplines, if any, in which you have such a rapid progress in terms of power and abilities you gain every year. Okay? So, and then there are other plots again to give you the sense about, it's not about the scale which increases very fast. It's also, it's a heterogeneity of devices you have to deal with. Okay? So if you look here, this is a slide, I think, borrowed from Kubi and who borrowed from Dave Kahler. Basically, this shows that, you have a lot of computing devices today which range all the way from MEMS, sensor networks, which you may not even be able to see with an naked eye, to, to data centers, which hold, the biggest data centers today, they host hundreds of thousands of machines. They can. Okay? So it's a huge disparity. And of course, in the middle, you see here, of course, your phone, the car. So, cars, pretty soon, it was this study that actually, if you look in segments of markets, probably the cars are going to use the most of the processors which are built. So do you know how many processors do you have in your car? Assuming that it's a reasonable new car. 1, 5, 10, 20. So how many of you believe it's less than 20? And how many of you more than 20? Of course, the way I framed the question was the answer was reasonably obvious. Yeah, so you are right. So actually, it's more than 20. Actually, the newest cars, they have something between 50 and 100 processors. And they have kilometers of wires to connect them. Okay, so it's a very complex. So again, the main point of this slide is that you have a huge variety of devices and huge heterogeneity. And when you build these operating systems, which are going to manage these devices, you have to cover all of this very wide spectrum. The other way to look at it over the time is this inverse of the Moore law, if you have to look at it, in which is that how many people per processors do you have, or the other way around, CPU per person, right? So initially, again, in 50 years ago or 60 years, you had a lot of people. You have only a few mainframes, even in the entire United States, and you have a lot of people programming on the same mainframe. As the time goes on, they become cheaper. The computers become cheaper, and they proliferate, and the number of person per computer decreased. And right now you have what? We are going very fast approaching a point in which you have maybe hundreds of processors for each individual, right? Again, even today, if you have a car, if you have, your laptop, your phone, and whatever, you have quite a few processors you are using every day. Okay. Now, usually the Moore law, when you talk about the Moore law, there is another law, which is Joyce law. This is a co-founder of Sun Microsystems, which it's sometimes confused with. So this law basically says, okay, what is the performance, the growth in the performance? Okay, and the growth of a performance, Joyce law, was very similar. So a very similar law is Moore's law. That is, the performance of a processor will increase exponentially in time, more precisely, 50% per year. So again, we'll double something between 1.5 years and 2 years. Okay? So the interesting thing here is that, this worked well for a long time, you see. But here in around 2002, it stopped working. And this green line represents what would have been the performance if the Joyce law were continuing to work. So now you have a gap between the predicted performance by Joyce law and the actual performance. It's 3x, and this was 2006, and actually it's growing. So do you know what happened here?
90 nanometers. 90 nanometers.
This is what the.
Pitch.
Yeah. Okay. Yeah, that could be the easiest. Well, right now actually there are 65 nanometers and even lower.
That's a lot. They come with a lot more trouble shrinking past 90. 90 was the last easy die shrink.
Yeah. Although if you look at all the flash memories, they are lower than 90 now. Like, yes. Clearly, it has an impact, actually, about cost effectiveness and so forth. But
I think it's starting from 130 nanometers. Well, 9 nanometers would be the first one, but they couldn't scale BGP down anymore after 130 nanometers because, and so VDD, the power density would go too high, so you have
excellent.
Just burn up.
Yeah, so the big problem was the power. Okay, so the power, in order to scale the performance up, you need tremendous power. And
this cuts off at 2006, and that's when Intel migrated off NetBurst. And NetBurst was one of those architectures that had that problem. But their core architecture doesn't have. Their quad-core new i7s have as much power as the high-end Pentium 4s in 2005. So does this still work today?
okay, so there is some discussion again about the technology, and you mentioned that today with the 4 cores, the Intel technology reduces the power consumptions to the level of Pentium 4. However, the high-level point is still the same. The main limitation, which was considered to be today, is the inability to scale the Joyce law, to scale with the Joyce law in terms of performance, is the power consumption. Okay, and if you look actually at the frequency of the chips, when you buy a computer today, in terms of frequency, you are going to have what? 3 megahertz, a little bit more, and so 3 gigahertz, a little bit more. This was a case last year. This was a case 2 years ago. 10 years ago, you actually, every year, you have a higher and a higher frequency. So, however, while Joyce's law is no longer, so to speak, true, the Moore's law continues to be true. So the number of transistors per chip continues to increase and to double every 1 year and a half. Okay? So, and what you are going to do is these chips, which have so many transistors. So people, what they do, as you know, they build multiple cores, multiple CPUs on the same chip. And this is an example back in 2007. It's an Intel Intel chip with 80 cores. And actually at Berkeley, there is, this comes also with a big challenge. What will be the big challenge here? You have 80 cores. The big challenge will be, what do you do with them? How you are taking advantage of them, right? So it's a programming challenge. And actually, there is a lab here we call SPAR Lab, which Ben is part of it, which tries to address this challenge about how to make it easy for the programmer and for the applications to take advantage of when having many, many cores. Okay. And again, like we discussed, what you do with them, and what do you mean? How many cores are enough? Okay. 64, 128. If you have applications which can take advantage of them, people are going to cram more and more cores on the same chip. And what you are going to do with them? That's a question. That's a big question, right? How many applications do you run at the same time on your computer, on your PC? Maybe video, audio, word processor, browser. But then if you have 80, what you go with the next? It's a little bit of, you could laugh a little bit about that. But actually, this is pretty realistic. Actually, a lot of research today proposes to have, to use all these cores to do a lot of background work, which otherwise you wouldn't do because you have been too high overhead for your application. But now these are sitting there idle, these cores, so you could do a lot of fancy stuff. Any questions? So, so going back to this point about the power, okay? So this is a plot showing in easy to understand terms, what would have been the power, the density you need to have if you were to follow the Joyce law. Okay? So again, in 2000, at the end of the last decade, it was a hot plate. So, that was a CPU, temperature. And then you go all the way, so to 2008, it will be something like a rocket nozzle. Huge power. What you are going to do with it? Right? It's not great to have such a machine running at such a high temperature. There is another flip side. Okay, the flip side is a battery life, right? As you know, the battery life, the battery technology doesn't progress as fast as the other technologies, like, again, performance or the number of transistors on a chip. Okay? So if you think about your phones, the big question there is how much computation power you can put on that phone, and very soon you arrive at the main limitation being the battery. Okay? So in this domain, then there is this big trade-off of the portable devices. In the domain of the portable devices, there is a strong trade-off between the battery life and the computation power. Okay, so any questions so far? So what is a computer system? So first of all, when you define a system, first you have to specify what are the entities from which the system consists of. And what are the main entities when you are talking about computer system? So the CPU, of course, what else? The memory. And then besides those, any computer systems has to deal with a lot of input-output devices. Keyboard, display, printer, mouse, disk storage, and your touch screen. Okay? And actually, a lot of complexity is there in dealing with these input-output devices. Okay? And then your application has to handle and to coordinate the interaction with these input-output devices. And not only that, you are going to have applications. And different applications want to use different resources, different input-output devices. Maybe sometimes simultaneously. So you have to have a way to decide which application is going to use which device when. And now we start to see a little bit about what the operating system has to do. We'll go into more details. Another way to look at, and if you look only when you have all these devices and all these entities in a system, you need to organize them, okay? And you have to organize, and in this organization, what is your overarching goal? Your overarching goal in this organization is to try to simplify the system, to simplify the interaction between the components, and to make the life of the people who use the system easier. The people who use the system can be the programmers writing the application, and eventually the user. Okay? So this shows an organization, the structure of the memory, different memory entities. So if you look on the memory, it's a lot of complexity. Right? You have the CPU. The CPU has some registers, then has a cache, local memory. Then there are maybe two levels of another level of cache. Even if you have a processor with multiple cores, you can have right there on the chip, you can have two levels of cache. One per core and one for the entire chip. Then you have the DRAM, then you have the disk, and so forth. Okay? So quite a bit of complexity. And you need to deal with that. And actually, the operating system will do it for you. Any questions? Okay? So really the overarching, the theme, one of the main theme of this class, as you'll see in all the next slides, it's about dealing with complexity. These systems are extremely complex. Okay? When you say the Moore law, when it says that the number of transistors doubles every 1.5 years, this tells you what? Is more complexity, right? You have more things to do, you can do more things, you have more things to deal with, right? You used to write programs for one CPU. Now you have to write programs for more CPUs. Okay? And looking from another perspective, you see that you look at the operating systems and you look at the lines of code as a measure of complexity. Okay? And just to put things in perspective, So this is Vista. Actually, I do not have numbers for Windows 7. I looked for them, I couldn't get. So if you have, anyone has lines of code in Windows 7, just let me know. But the point here is that Vista has 50 million lines of code. Now, at this other extreme, you have the Space Shuttle. The operating system of Space Shuttle, which is doing launching, landing, all of this stuff. So that's what? This is probably, again, between 2 and 3 millions. So it's a factor of 20, over 20, the difference between the Space Shuttle, the entire software, and Windows 7. And by the way, this cannot fail, right? Which is not true for, at least for Vista was not true, right? So, okay. And you see, somewhere in between, you could see like Solaris when was, under 10 million lines of codes, and Windows 98 and even Windows NT were significantly smaller. Right? Here is Linux. It's respectable. 30 million lines of code. Okay. So now we laugh at Microsoft, but there is a reason for this complexity. What is the reason? Huh?
Positing. The pretty interface.
Pretty interface. Okay.
That's 10 million.
10 millions on top of that. Okay, good. What else? Is what? Can you speak? Drivers. Okay, to handle all these I/O devices. Okay, good. So please, can you speak a little bit louder? I do not hear. Very good. What else? Okay, that's a security model in what? In Vista? Okay. Okay, I think it's, yeah.
Now you have more hardware resources. You might as well be using it.
That's very good. More hardware. So this all of them are, all your comments are very good, pretty interface and so forth. But two things in particular I want to emphasize here. So one is indeed the backward compatibility, right? Because you want to, at least Microsoft wants to, be able to run all programs on the new operating systems. So if you want to add and change the way things you do, you can do that. You are free to do it. But at the same time, you have also to support the old things, the old applications.
Is that important? Because it's not necessarily, Apple dropped PowerPC support.
That's excellent point. That's excellent point. Apple is not doing that. So Apple periodically drops the support for the old operating systems. It's doing much more so than Microsoft. And this allows them to keep the operating system simpler and more robust. However, the market for the Windows and for the Apples is different. So people who have Macs are more likely to upgrade to the new applications than people who have Windows, and many are very cost conscious. Okay? So that's one of the strengths of Windows over Mac, the backward compatibility actually. And many, corporations and so forth really appreciate it. They don't need to spend a lot of money for the newest software. They can run the old one. Okay? The other thing is about, which also is a good example to contrast the Mac OS with Windows, it's a variety of hardware the Windows machines handles. I'm not sure that in this room, for the Windows machine, Windows laptops, there are two the same. Even if they are the same model, if you buy Dell's computers, a few months apart, the same model. The component inside could be different. Okay. On the other hand, something like Mac OS is much more controlled architecture, right? It's a much more closed system. So the variety of hardware you have to support is much lower. Okay. So now it's let's see about take a case study to just see what are the challenges of an operating system, and let's think about this. It's an interesting I think case study here. It's a Pathfinder, the Mars rover. Okay, and this was a thing which was I think was the last decade, and it was very NASA sent on Mars. And it was having these airbags when it landed. It was actually, I found on YouTube, of course, I found this just to give you for fun. Okay, where is this? So this is what happened, right? Very, very interesting. Low technology, very effective. Pretty cool. So anyway, so the question here is about, okay, so you want to have an operating, you need to write an operating system and application to control this rover. So first of all, let's look about what was the hardware and the software. So actually the hardware was 20 megahertz processor. You probably never use something with such a low frequency. 128 megabytes of RAM, and the operating system was VxWorks. This is a real-time operating system. And this operating system has to control a variety of input-output devices, cameras, scientific instruments, and so forth. You need to move the rover to points of interest from which you get data and make measurements. And there are many processes working together. So what are the challenges with doing this? So you have to design something like this. What are the challenges?
It's on Mars.
It's on Mars. Excellent. So what does it mean?
Far away, so it takes a lot.
It's far away, right? What do you do when your computer hangs? Reset it, right? What do you do with this guy when it hangs? Okay. By the way, even if you can send its commands, how long it will take? Very good, very good, very good. Yes, it takes between 2 minutes and 14 minutes, depends on where the Mars and Earth are positioned. Okay? So, even if you see that something happens, right? This is going, to fall down or whatever, it will take you 2 minutes. Actually, it's more because it's round trip time. Between 4 and 28 minutes to give a command to this guy. And what else? By the way, for this guy to receive commands, what should happen?
Receive the signal from Earth.
The antenna has to be oriented toward the Earth. So there are some pieces of software on this rover who basically cannot fail, or if they fail, there is an auto reset. And you can get in a consistent state after that reset. It's automatic reset. Right? So these are, again, the antenna has to be always positioned the right way in order to get commands to send data back to the Earth. It has to be, again, the movements, when you control the movements. If you are on the edge of the canyon, you need to know about that, and you need to react. Okay? So, and that's what's actually the reason for using this, hardware and software. You never use the latest generation of software and hardware in this kind of equipment. Right? You use the older ones, you know for sure that there are very few bugs, if any. Okay? Still, so this mission was it was a big success. It had problems. Do you know what was the problem?
Did the tape drive fail?
Hmm?
Did the tape drive fail?
What failed?
Part of the tape drive? Did it fail?
Yeah, actually, no. It was so the problem manifest of having it was continuously resetting, auto restarting at some point, and the reason was what was called the priority inversion. Okay, so priority inversion, you have processes which have different priorities. Have very simplified. You have a low priority and a high priority. And the low priority gets a lock on a resource which is required by the high priority resource. Okay? Now the high priority process is going to preempt the low priority one. Okay? So the low priority one cannot finish its work and release the resource which has locked. So you have basically a deadlock. Now, the operating system here is smart. It's looking at this resource, sees that it's a lock on that, nothing happened for a long time, and then restarts the entire system. Okay, that's how you saw this all, people saw back on Earth, they saw the restarts. Okay? But it's again, go back to say, how hard is to design software, right? So again, this is 128 megabytes of RAM. How many lines of code can you fit there? Not many. Okay, and it was very well tested, and still you have these issues. Still, in the end, this was not a tragedy, and it was a very successful mission. Okay. But you could see from this example how many challenges you need to answer when you try to design an operating system for only one application. And this application was gather information from Earth and send back to Earth. So how do we tame the complexity? And when I say complexity, what do we mean? So what we mean by complexity is, again, it's a diversity and heterogeneity. I have different CPUs which have different abilities, different power, different amounts of memory with different properties, latency, how big they are. Different type of devices, some of them very different, keyboards versus touchscreens, sensors, cameras, fingerprint readers, different networking environments. Okay, so if this is what the hardware you are going to provide, you have. This is a hardware you are provided with. And now there are questions. So you are the programmer and you want to write an application. What do? Are you going to write one program to perform many different activities? Like in the previous case, are you going to write one program which is going to move the rover, is going to collect samples of the soil, direct the antenna, sending back the information, and so forth? Or are you going to write many of them? We somehow interact. Does your program have to be altered for every piece of hardware? Right? Are you going to write the program a little bit different for every piece of hardware? Right? For a new laptop, you are going to modify a little bit your program. Does a faulty program, if a program crashes, what are the implications? Is that going to crash every other program on the machine? And related to that, does every program have access to all hardware or not? So this is a legitimate questions you have to answer before starting to design your operating system. And based on the answers to these questions, you are going to make one design decision or another. Okay? So here is the way one way to look at the operating systems. Okay? So let's do a mental exercise. If you wouldn't have an operating system, what do you need to do? You have the hardware. Like we discussed, every computer almost have a different hardware. So you write an applications. What do you have to do? Yeah. So you basically have little choice, but adapting your program for different machines, for different hardware. A new hardware comes up, it's produced. Oh, you need to go back to your program if you want to run on the new hardware. So the operating system simplifies that. It decouples the application from the hardware. So the operating system provides to the application an interface which abstracts away the differences in the hardware. What is the advantage of that? Now you can write a program for the interface, which many times is called virtual machine interface, which is provided by the operating system. Okay? So you do not care about the particular hardware, at least in most cases. So the operating system provides you this nice interface and environment which abstracts away all the ugliness underneath. And then there is another interface between the hardware and the operating system, which is also important. Right? Because yes, you don't need to change your application, but if a new hardware is released, then what you are going to do? You are going to change your operating system? Are you? What happens when a new printer is released? What do? What do you get? Very good. So actually there is a part in the operating system which you get changed. These are device drivers. Right? But the device drivers provide you also a nice interface so that most of the operating system remains unchanged. Okay. So one of the big questions always we are going to go over and over again during this class, and you are going to go in other classes as well, is what is the interface? What is the interface provided by the operating system to the application? What is the interface provided by the hardware to the operating system? And designing a good interface is very hard. It's not easy. You'll appreciate that in time. Okay? So this is a slide making the point here that, again, trying to, the interface, what is the interface, for instance, between the hardware and the operating system? One part of the interface is represented as the instruction set of the machine, because this is what the operating system uses to manipulate and to control the system. And this actually, that the other things, this was at that point also showing in the original picture, this was how Intel was supporting Microsoft here, many applications. So it's again, this is, I cannot emphasize enough how important are these interfaces. Right? You are too young, probably, but it's again one of the main. The x86. It's a very complex. It's a very complex. It gives you a complex set of instructions. And why is that? It's also because backward compatibility and some decisions which are made very early in the design, which proved to be costly. Like, for instance, the instructions are not very symmetric. With similar instructions, you couldn't do the same things. Okay? So going back to the virtual machines, the virtual machine, it's a software, it's a layer of software which emulates an abstract machine. And this abstract machine, it's much easier to operate with. Okay? It gives basically to the programmer, to the application, the features it wants. Again, by abstracting away the diversity of the underlying hardware. Okay? So here is an example of what a virtual machine interface can provide. To each process, it can give the illusion that it has all the memory for itself, it has all the devices for itself, the device drivers, all the printers have the same interface, and they are more powerful even than the raw hardware. Right? It's pretty easy to see how this will ease your job as a programmer to design an application. Let me give you an example. It used to be in the past that, for instance, when you write on the display, the application will have direct access to write one bit, to change the color of a bit on the display. Now, you write that application, you write a program in that environment. And your program is not the only one to run. What you are going to do? What you are going to do if another program, after you just set up the pixel, is going to reset it? Yeah? It's not easy. So that's why here the abstraction was a window system. So the application has a window, which may be in background or a foreground, can be minimized or not. But when you write a pixel there, you write on that window, which you own. It's your window as an application. You don't care if the other guys have other windows. Okay? then what you like to else to provide? You want to provide fault isolation. What does it mean, fault isolation? A process cannot impact the other process. If another application fails, it will not fail, it will not impact your program. Okay? And of course, the bugs shouldn't crash the entire machine. And then it's also protection and portability, like Java, JVM. Like Java was built with a promise you write once and runs everywhere. Okay? Again, it may not have been successful, fully successful in achieving that goal, but still, it's a very nice goal to have, which makes you easy to develop applications. Right? And there are other environments like Adobe's Flash, ActionScript, and so forth, like Silverlight now, which tries to achieve that goal. Okay? So this is just an example about, just to put more detail into what I said. So here it's an example in which you have a Linux operating system over the hardware, and above the Linux you have a virtualization layer, such that like VMware, provided by VMware. How many of you have used or are using VMware? Very good, very good. And the VMware will provide an environment, will provide the illusion of an entire machine on which you can run a full-fledged operating system. Like FreeBSD, you can have a FreeBSD, Windows NT, Windows XP running side by side. And of course, you can have application running on the host operating system. Okay, so this is hopefully an atypical course. It's the first course, so it took me much more time than I intended. But anyway, so let's talk a little bit about the course administration. So as I said, it's my name, Ion Stoica. My office hours, the tentative office hours are Tuesday, Thursday from 2 to 3 p.m. And your TAs, if you can stand up, it's Matei, Andy, and okay, I have it here, or it's on the next slide. I think yours is from 10, right? And Ben. So they are fantastic TAs. Again, you are lucky, and I am lucky to have them. And these are their emails: CS162, TA, TB, and TC. So TA it's Matei, TB is Andy, and Ben is TC. Correct? That's correct, Andy?
Yep.
The website, you know where to find it. We are going to use a news group, so please check the news group often. And we'll probably also have a reader, I'll announce. The class schedule, forget it, it's Tuesday, Thursday. So that's so the please try to attend the class. I know that it's a little bit late in the day, but please try to attend it. The lecture notes do not have everything we are talking during the class. And 5% of the grade is from class participations. The section, very important. You are going to find, to get a lot of information from the sections. The section assigned to you by telebeers are temporary. So we are going to have, like I'm going to discuss in the next slide, we are going to have projects. And the project groups will have between 4 and 5 people. Now you are assigned by telebeers, you are assigned in a section. You are going to have until next Friday. I'm going to remind you a little bit later. For next Friday, you need to try to find among your peers in the same discussion section who will be your project group members. Okay? So the first thing, you look at the telebeers assignment. If this doesn't work for you, you send to us preferably more than one option. Okay? Because we want to balance among the discussion sections the number of people. Okay? And then, once you are going to be assigned to one of these discussion sections, you are going to figure out, to try to pair for your group project group. Okay? Any questions? Yes?
Just so we're clear, so we form a group and the group picks a section, or do you pick a section?
You can do both ways.
Okay.
If I were you, though, if I know so you see, if you know now, you know who you want to be on your group, the group is already formed, clearly you would like then to make sure that all of you will send the preference for the same discussion section. If you do not know, you pick the discussion section and you find group members later. Yes?
Oh, I just want to like we form a group already and then all the members are in the same discussion section. Are we going to move on?
It's highly preferable to be in the same discussion section.
Yeah, right now we were registered on the same.
Excuse me?
Right now we were registered on in the same discussion section. So you said that televisions are temporary. So is there any possibility of the entire group will be moved out to another section?
It could be. It could be. Please send the emails, and it's again. We need to. It's a trade-off between that, and we want to keep some balance between the discussion section in terms of the number of people. Yes.
Are all the discussion times set in stone?
Excuse me?
Are all the discussion times set in stone already?
Yes, I'm going to go. Let me discussion times. Okay. These are the ones right now. Yes? Between 4 and 5 people.
Is there any CS provided source control, or should we set that up ourselves?
We are going to have that. Just wait for announcements.
So
We haven't decided on that. We still have time until the first project. Any other questions? Okay, the textbook. It's Silvershas, Galvin, and Gang. It's the 8th edition. There is an information link on the course website. I encourage you to go at that link and to see additional materials. You have appendices, sample problems, and so forth. And one of the questions is, do you need only editions 8? The answer is no. We are, if you have edition 7, that's fine as well. When we give the reading on the class webpage, we give the readings for each lecture, both from 8s and 7s. Okay, so what topics are we going to cover? So the first week will be a little bit, again, general overview of the operating systems and some history, background. Then we are going to talk about process control, thread synchronization, and so forth. Advanced topics, we'll see whether we hope to have a lecture in which we can have advanced topics. And we can tell you some of the research which is hot in operating systems and in Berkeley. Grading. So there is one midterm and one final. And then there are 4 projects. Each project is 12.5%. And then it's a class participation we discussed about. The first 3 projects, it's about building key elements of an operating system and will follow very closely what we teach during the lectures. So you build a thread system, implement multi-threading, and memory management, caching, and virtual memory. The last phase will be something on, we haven't decided on the project, but will be something on probably distributed systems. We hope to have some project which will be about, cloud computing. Okay? Any questions? Policy. There will be no sleep days. Okay? Hey, it's fair for everyone. Okay? It's the same rules for everyone. I had in the past, actually not for this class, but for E122, we had in the past the concept of sleep days. It never worked well. It's very hard to account for them, especially when, in the middle of the semester, maybe, some people drop, you remain with a group of 2-3 people, and then you want to merge the groups and so forth. What does it mean sleep days then? This is very clear. You are going to have, each project has 2 phases, a design phase and a code phase, when you need to submit the project. The design phase is very important. Okay? And for the design phase, really try to not be late. Okay, the 10% off per day after deadline applies really only to the final project, the code, complete. For each phase.
So we have a design document?
Yes, you are going to have a design document, you are going to submit, you are going, your TAs they are going to look over the design document, it's going to give you feedbacks and so forth. The reason you don't want to be late with that is because then you don't have time for coding.
I mean, after returning the code, one day after returning the code, we're turning the final design down, right?
Excuse me, after?
We're going to turn the final design down one day after returning the code.
So basically, you have a few days. You have I don't know 1 week, maybe 10 days for the design, and then you have another 10 days or so for the coding. Okay, does this answer your question? If you look on the class schedule, you'll see all the dates. Okay, so the objective of this having a teams of 4 or 5 members is to simulate industrial environments. By definition, engineering and actually software design, building the projects requires to work in groups, in teams. The TAs, and then you have a manager. The TAs will act as your manager. Okay? He's going to review your design, give you feedback, okay, and then he's going to grade you. Yes?
Does the TA also take us to dinner, perhaps?
If you are nice, maybe.
You can take the TAs to dinner whenever you want.
Okay, so one challenge you need to be aware. How many of you work before? How many of you work in project groups before? Okay, so then I can be fast here. So again, pay attention to communication. The communication is very important to your colleagues, both in understanding what your colleague says and in making you understood by your colleagues. Okay, you want to start early to engage other people in the team. You don't want to wait until the deadlines, because in many cases, if the project is not successful, it's because of communication. You are all smarts here. Okay. You must document your work. Okay, and as I said, you need to communicate with your TA often. We'll be more precise as the time goes on about this. So this is typical lecture format. It's not today. Today was not typical. So this is the first time, to tell you the truth, I'm trying this. Usually I divide the lecture into two with a break. But this is probably even better. You'll even so it has 2 breaks. The lecture will have 2 breaks. It will be like 20 minutes, then a short break. The first break will be about to do this kind of announcements. Then it's another 20, 25 minutes, it's another break. And that will be a break you can, go, drink water, whatever. You can move around. Then it's another 25 minutes, after which we are going to conclude the lecture. Okay? And it's again, this, it was, it seems there are quite a few studies done about maximizing the attention of students, and it seems this is what is working. People come happy to the class, relaxed. They're going to spend, they are going to be willing to pay some attention for the next 20 minutes, but then, I am just talking, and you are going to, at some point, it's that much you can take. So then we are going to take a break. Okay? And then, we repeat one more time, after which we finish the lecture. Questions? Interactivity. I really would like this class to be interactive. Okay? Many questions. This is good for everyone. For you, for your colleagues. Computing facilities. Before you leave, you don't leave before taking one of these accounts. Okay? Each of you is going to get one account. Most debugging and development can be done on your ES account. You need to make sure that when you run the program, you are running on your CS162 account. You can develop on your computer at home. That's fine. But when you run it, when you test the program, finally test it, you need to do on the instructional account, because that's the account and that's the platform on which you are going to be graded. Okay? So make sure when you get this account to log in to verify that everything is fine. Project information, again, we are going to give you more information as we go ahead. We are going to use Nachos. How many of you knows about Nachos? Okay, good. So at least you are going to learn something, right? So the Nachos is this. It's basically an operating system written in Java, which makes it easy to develop and debug. There are trade-offs. This is not a real operating system, okay? And on the other hand, it's much easier to develop in it. And hopefully it captures all the concepts, and it will teach you all the concepts well. And again, newsgroup, read it regularly. So we have another 6 minutes. So let me try to make more progress on the material we have. So today, unfortunately, again, we don't have the second break. We'll try to do it starting with next week. So what is an operating system? Now, after all this almost 1 hour and 15 minutes, you should have a sense of what it is. And people try to define it. It's just something which is not easy to define it. So, when you see this kind of definition in your textbook, you can see that it's hard to define, right? So in Silversatz and Gavin basically say, okay, an OS is similar with a government. Okay? What does this mean? What does a government do?
Take taxes.
Take taxes. Yeah, that's one view. What else?
Military.
Hmm?
Military.
Military. Okay. Defend. Okay. Who's the
Keep order.
keep order? Very good. Very good.
Smart educate. Oh wait, no, never mind.
A little bit more positive. Okay, so one of the functions is indeed the traffic cop and coordinator. So what does it mean? As you saw, you have a lot of resources, different resources which are part of the system. And you have different applications trying to use them. So what do you need to do? You need to decide how much you allocate to each resource, how much resources to allocate to each program, and when, and for how long. So when there are multiple programs requesting the same resource, you need to settle the disputes. And you need to prevent errors and improper use of the computer. What else? A government, what else gives you? It can be a facilitator, right? It provides the facilities that everyone needs. You can see this as an overhead or not. Okay? Things which are related to social services. Things like healthcare. These are the kind of things a government could provide or not. In terms of the operating systems, these are the standard libraries, which makes your life easier. You don't need to write everything from scratch. Windowing systems. Okay? And there are some features which reflect both tasks. Like a file system. It's a facility. It's needed by everyone to read and write your data. At the same time, the file must also be protected between different applications. Now, what is in an operating system? What does it fit in? Memory management, we would agree that memory is a very important resource. It has to be managed. I/O management, the same. Right? CPU scheduling, communication. Does email belong to the OS? So don't you have an opinion? How many of you believe it does belong and how many doesn't? How many does not? Okay. So when we say communications, there are different layers in the protocol stack. Okay, all the way from the physical layer to the application. Email is an application. Usually it does not belong to the OS. Multitasking, multiprogramming. How about file system? Does it belong to an operating system or not? Yes, good. Multimedia support. Does Flash belong to an operating system? Does QuickTime belong? User interface, internet browser. Does it belong? You know very well it was an antitrust against Microsoft 1 decade ago or more, which found that the internet browser should not be part of the operating system. Is this only interesting to academics? That's always a good question. So now, it's exactly, there is no universally accepted definition of what is in an operating system. There is a liberal definition which basically says every single vendor ships with your order isn't part of the operating system. So you get a Dell or a Mac, everything which comes with is part of the operating system. But what you get, it varies widely, right? You get browsers, you get the chat applications, right? There is some definitions of which is, people are agreeing with it, and that it's a kernel. What is operating a kernel? The kernel is part of the operating system, which runs at all times on your computer, right? And this is kernel, OS kernel. This is one definition. Is the definition. Everything else outside the kernel is either what is called a system program or an application program. Okay, and it's 5 p.m., so I'll stop here. Please.